Can continue. I hope you have enjoyed the lunch. We are a bit late, so I think it will be good for both of you. And now we continue with the next speaker, which is Andreas Dilger.
Hi, thank you. Now I'm me and not Artem anymore. So today I'm talking about Lustre 2.16 and upcoming features and development. And so, as Peter said, the 2.15 release was made in June, I think. And so we're well underway in the 2.16 development. James, who's here, is busy working with the IPv6, and that's also sort of co-developed with Neil Brown in SUSE. And we also have another feature, optimized directory traversal. It's improvement of stat ahead. And I'll be going into some details on some of these. 2.17 is a new feature, quite interesting, is client-side data compression. And in some regards, we hope that it'll be very similar, reusing some of the functionality that was added for client-side data encryption. But it's been a project that's been underway for quite a number of years. Started several years ago with the University of Hamburg, and now we have somebody developing it at WAM Cloud to finish off that work. As well, there's well underway for metadata write-back cache. And we have some early discussion of features. Erasure coding is something that had again started quite a number of years ago with a prototype, and Oak Ridge is taking over the development of that feature as well. We're talking if we can start implementing some components of a Lustre metadata redundancy to allow reliability for MDTs. So on the LNet side, in 2.15, one of the features that landed that was quite interesting, worth mentioning here, is multiple connections, multiple TCP sockets for Ethernet. And so we found with high-speed Ethernet, 100 gigabit and faster, that we weren't able to saturate the network links with just one connection, and that's because of the high CPU usage for TCP connections. And so by having multiple connections per peer, we can have the connections working on different CPU cores, and that's significantly improved the throughput on TCP connections from a single client. And we have a heuristic that's relatively good in terms of auto-selecting the number of connections. You can always specify this manually if you want, but the default that we pick for 100 gigabit is 4 connections per peer, and that seems to be reasonable. And with increasing number of connections, if you have a huge number of clients or connecting to one OSS, for instance, it's potential that you could run out of TCP sockets, but I don't think that there's people that are running 15 or 16,000 TCP clients in one network without routing or anything. So it's probably going to be okay, but you can tune this manually. Another feature, LNet selection policy, also called UDSP, allows you to specify rules. So if you have dissimilar networks that you want to use with bonding, but you want to prefer one network over the other for some reason. So if you have, let's say, InfiniBand plus Ethernet going into one host, you can say, route all of the traffic over the InfiniBand if it's available. But if the InfiniBand fails, then fall back to Ethernet. Or you can select, if you have routing, select one interface over another for connecting. In 2.16, like I was saying, IPv6 support is probably one of the biggest features. And that's something that we've been wanting to do for quite a number of years. Neil Brown had started that development before the 215 feature freeze, and we'd started some of the infrastructure work to land in 215, but the majority of the functionality is going into 216. And so this is the work for implementing the LNet layer support is, I would say it's largely done. It's not quite all landed, but you know, the code is there for LNet. There needs to be some more development done up at the Lustre level in terms of configuration logs and tools and things like that that handle NIDs so that they can parse and you know, print out you know, IPv6 NIDs as well as the configuration logs, you know, have you know, records that some of them are fixed size that hold a NID in them, and in terms of doing routing between IPv6 and non-IPv6 clients, there has to be some compatibility work done there. And as well, there's an ongoing effort by mostly Chris Horn at HPE doing a lot of work improving reliability of multi-rail peer discovery and health to improve, you know, corner cases in that functionality, steady series of patches. As well, like I mentioned, the dynamic server node addressing, right, to be able to handle, you know, clients with DHCP or servers without, you know, with the server, you want to change it to a different network. Right now, you have to rerun the configuration. It's a little bit cumbersome, but you know, we want to be able to dynamically address you know, interfaces on a server. So if you add new interfaces, then the clients would be notified transparently, and instead of having to rewrite the configuration each time. In terms of work on the client side, there's been, you know, some interesting new features. The GPU Direct for NVIDIA GPUs, and so we can do RDMA directly into GPU memory, and so that it improves the performance somewhat, not dramatically, but the big win with GPU Direct is it avoids CPU consumption, because you're not running over the inter-CPU links to route your data, and you don't use CPU cycles processing every byte. The drawback is that right now, if you're using GPU Direct, you can't do data checksums because we compute the checksums on the client, and you wouldn't be able to do encryption and things like that that involve the CPU. But for most workloads, that's fine. As well, a number of performance improvements in terms of direct I/O and client-side encryption, which Sebastian's already talked about. Another little handy feature that Oak Ridge did is LFS find minus printf, and so then you can have it print out specific fields from a file. If you're looking, you know, you do LFS find to find a bunch of files, you can say, oh, print me, you know, the size and the stripe count and the project ID or something like that, and you know, instead of just printing out the name, right? And going forward with 216, one of the things that James said he would do is improving the O2IB to be, you know, more acceptable to upstream kernel developers, because we're using the OFED in kernel OFED in a way that they don't like it. So that needs some cleanup. Encrypted file, backup, restore, Sebastian's already talked about. Buffered I/O performance, was in flight. And just, you know, general cleanups in the client code. One day we hope it will be, you know, again, submitted into the upstream kernel. It's not a huge priority for us, but, you know, it would definitely make it Lustre more available for, you know, ease of use for various users. And it, you know, we have such, you know, the number of features going into Lustre is, not growing by leaps and bounds, and we have good protocol compatibility. So even if the upstream kernel isn't getting all of the latest features, we do have fairly good compatibility in that front. On the back-end server side, there's also, quite a bit of work being done. As I mentioned, MBALIC improvements. On the ZFS side, the D-RAID feature that we developed at Intel, was finished off with help from HPE and Lawrence Livermore, and is included in the ZFS 2.1 release. And that's the default. ZFS 2.1 is the default for 2.15 and going forward. Also, I mentioned a bit under the MBALIC presentation that OST sizes are growing, not just because individual disks are growing, but because of a declustered RAID. You want to have more and more disks in a declustered RAID group, and so it's essentially the size is growing kind of exponentially. The individual disk sizes are growing, and in order to keep the rebuild time constant, you have to increase the number of drives in a declustered RAID group, and combining that, is sort of exponentially growing the size. So we're, targeting 1 petabyte OSTs, but it's, entirely likely that we will need to have, 2 petabyte OSTs in a year or two. So with that, the large OST sizes is that we'll have, billions of objects per OST, and the on-disk data structures are not really suitable for that today. We have 32 subdirectories per MDT, and while that's acceptable, it gives us about 300 million-ish objects per directory tree. That's still quite a lot for one directory. And having a wider fan out, having 64 or 128 or whatever object directories doesn't really help, because you're doing random I/O within the blocks of those directories, and so you're not getting any efficiency. So rather than keep on scaling the number of directories, we're actually going to move it to having more directory trees, so that each MDT will create at most 32 million objects in one directory hierarchy, and then move to a completely new hierarchy. And so the old directories will stop being used, and you'll get a whole new set of directories. And so that is more efficient over time, because the old directories will fall out of cache typically, because you're not using them as frequently, and we can still have aggregation of creates in the new directories, and so it's more efficient. And this needs a little bit of a protocol change, but that work is underway. Other improvements for LDiskFS with trim on flash devices, and the parallel FSCK, I'm not totally sure we have somebody working on that anymore, but PAS1 was, we did parallelization last year, and so, like Amdahl's law is, we've parallelized one part of it, now we're serialized on the next phase, and it's become the longest part of the work. On the MDS side, the biggest improvement in 2.15 was space balancing, and I think that that's a really important one. It makes D&E with multiple MDTs much more usable, because we're automatically balancing across multiple MDTs. And we have customers now with 40 MDTs, and they do multi-millions of operations per second, and they don't have to do any manual tuning there. Migration improvements on 2.16. We're trying to make the migration more robust, and we had to redo the hash function. There was a bug in the hash function, but because it's part of the protocol, we can't just fix the hash function. We have to make a new version, and so now we need clients and servers to understand the new hash. We'll backport it to 2.15, but it will be a while again before we can enable it by default. And just improvements in locking and things to improve performance with distributed transactions, because in 2.15 now that we're doing more remote directories, we want the performance of the remote directory create to be better. Currently, it's about 1/10 of the speed of a local directory create, and we're going to try and optimize that further. One of the new interesting features of metadata write-back cache. The development, it's a very large project, and so we're trying to get some parts of that feature to be included in an earlier release. And so we've carved out part of it. It's the batched stata head. And so we've introduced, in advance of metadata write-back caching, a batched RPC protocol change so that you can send multiple requests in one network message. And so, you can say get adder for 50 FIDs at a time, and then get all of the attributes back in a bulk transfer rather than 50 separate RPCs. And so that's more efficient from the network processing point of view. And you have lower latency. I mean, the individual RPCs are higher latency, but on the server side, you have lower latency because you're not doing a network round trip each time. And so what we're going to use that for is the improved stata head. And so stata head is considered like metadata read ahead. So if you're doing a read dir and accessing the attributes of each file sequentially, we start to prefetch the attributes in advance of the application requesting them. And that's good for ls-l and things. And so we're improving that further, the stata head, so that we can do breadth first or depth first search. And so rather than just doing stata head in one directory, we can do cross-directory stata head. And that will, speculatively prefetch attributes in a whole directory tree if we detect that a pattern like that is being used by the application. And so that's good for find and other kind of, browser type applications that are, accessing a whole tree of files. And then that's the preliminary. So in 2.16, we're going to do the stata head part, and then in 2.17 we're going to be landing more of the write-back caching, and so that's allowing metadata operations to only happen directly on the client. And so what's happening there is in new directories, or speculatively on existing directories, you can get an exclusive lock on the directory, and then the client will have complete control of that hierarchy of the directory tree. And so this is good for workloads, let's say Untar or something like that, where you create a lot of files on one client and then process it locally. And so that's useful for things like genomics and machine learning, where you untar a whole tree of files and then access a lot of the files quickly. And so with the write-back cache, the client can create without the round trip to the MDS for every file. And it's in our testing, it's been about 10 times or 20 times faster for certain workloads. And it still remains coherent with regular file access, because we have a lock on the top directory. And so if a client tries to descend through that directory, it revokes one level of the lock, gets exclusive locks on the next level of directories, flushes out the top level cache, and then, if a client is working its way down one directory tree, we only have to flush the cache on the one directory tree. And there'll also be like a time-based, aging out of files in cache, or memory pressure-based aging out of files in cache. And so it's all consistent and shouldn't need significant or any modifications to applications. It's just the question is, picking appropriate heuristics on when to use this interface. And finally, this is a little bit speculative, well, quite a bit speculative, but trying to improve the redundancy and reliability of the MDS, because right now, MDT0 is doing a lot of important functions, but there isn't any redundancy. And so I've been looking at what we can do to incrementally improve the reliability of the metadata service without, you know, having, I don't personally like having like a huge project where you don't get anything, you know, for 2 years, right? Because, you know, management priorities change or whatever. And so I've looked at, you know, what we can do. And so if the first phase would be trying to do, make some of the individual services that run on MDT0 more robust. For instance, the file FLDB, that's the FID location database, that's kind of the primary table that tells every client, you know, FIDs in this range belong to MDT0, MDT1, et cetera, et cetera. And each server, each MDT and OST has a partial copy of this data today, but only MDT0 has a full copy of it. And there's really no reason why all of the servers can't have a full copy. And then if one of them loses it, you know, that you should be able to fetch this data from any other server, right? Same thing like the quota tables are all managed by MDT0. You know, there's no reason we couldn't hash out the quota across different metadata servers so that we, you know, spread out the load. And some of the other project, the 1B that we're doing, improving the distributed transaction performance, that's something that we can, you know, do independently of any big project, and it will help all kinds of D&E operations. Because the more D&E that we do with the distributed transactions, the better, you know, the performance has to be so that it doesn't impact you badly. And once those things are done, we can start doing the 1C project, which would be starting to do mirroring of top level, like a root directory, so that you can access, you know, at least parts of the file system, even if MDT0 is offline, right? And because the root directory doesn't get modified very often, you know, having a mirror copy of it wouldn't impact the performance too badly, but we would definitely need to do distributed transactions for every update to that directory. And so I think that's what I have today. Any questions?
Thank you.
Is there any work going on with metrics or monitoring of Lustre? That hasn't been mentioned so far.
Yes and no, right? I mean, we do, you know, incrementally improve some of the statistics and things like that. One of the, you know, smaller projects is, I don't know if you know job stats, right? And so to add in per job BRW stats essentially, so that we get a histogram of the I/O patterns for each job at the server side. But I mean, the monitoring, you know, the overall monitoring of Lustre is usually deferred to some third-party tools, right? And so each, you know, vendor, and some people use Grafana or whatever, DDN has tools to do that, HPE has tools. And so we provide, you know, from Lustre we try to provide, you know, the useful information, and then how that gets displayed is up to somebody else.
Okay, thanks.
There's a question.
Yeah, it's me again. I just would like to add to that this field for the job stats is a little bit short.
Sorry, I didn't.
The field for the job stats is a little bit short. I think it's 32 characters long or something like that.
Yeah,
Yeah,
the job ID is, yes. So the question is the job ID is too short. And the unfortunate thing is, I mean, that's part of the network protocol, right? And so, you know, for many people, 32 is okay. It's not perfect, but we would have to change the network protocol to increase that, and that's not super easy. And it would be, you know, if we made it 128, that would be like 96 bytes of wasted space in every single RPC, and there's, you know, tens of millions a second, so.
Could you get a flag to turn off that warning from the logs?
Oh,
Because
yeah.
once I know it's too long, I know why it's too long.
Okay, yeah, I
Just
mean, it's true, yes.
feels
I mean,
logs
yes, we could.
uselessly.
I don't know if we fixed that, we might have fixed that, but if we didn't, please file a ticket so it doesn't get forgotten, and then we can make that like a one-shot error message or something like
Yeah,
that.
it's still there.
Yeah.
In the latest version I have it. So.
Yeah, okay.
Okay, it's okay.
I have a
Cool.
question. For the metadata write-back cache,
Yeah.
is there any client or user command needed to hold the lock of the directory for this, or is it magic?
No, I mean, I believe if you create a new directory, it will initially get an exclusive lock, right? So it will be kind of eager on the directory creation, but as soon as if you do have like a parallel workload where you create a directory and then, you know, all of the ranks create files or subdirectories or whatever, then you would have one extra RPC. But in a, you know, also a common case where you create a directory and then the clients create files within that directory, you know, you get the benefit of write-back caching. But there are going to be commands, LFS, WBC, you know, pin and unpin and flush and all of these different things to manage the cache state. But it's intended that it can be done transparently, but there's interfaces if you know better, you know, how it's going to work, right? And so initially, it's mostly going to work only for new directories, right? But there is the possibility to have the write-back caching work for existing directories. But what has to happen is the client would get the exclusive lock and then read in the full directory content for that directory so that it knows, you know, which names can be created and which ones exist already. And so that's going to be in a later stage of development.
And what about the recovery, in case of crash, are the creation lost, or?
Yeah, it's like any other crash if you haven't written it, right? But if you do fsync and things like that, then yes, they would flush and your fsync wouldn't return until it's written to disk, right? But it's true of any write-back data, you know.
Andreas,
Yeah.
I wish to be a little bit controversial and just ask you one thing. I've seen your presentations now for the last 10 plus years.
Yeah.
And one of the things I seem to see a pattern of is that the number of new features are getting fewer and fewer every time we go to a major release. Is this because there's no good ideas left, or is it just being more and more complicated developing new features?
I think there's a few factors there. I mean, yes, the code is you know, larger and more complicated. I think also, you know, Luster's getting very feature rich, and so we don't have, you know, there isn't a burning need for, you know, DOE labs to pay, you know, for new features to be developed all the time, right? We can run on the biggest machines without, you know, brand new features all the time, right? And so we used to have a dedicated, you know, team of 20 people developing new features all the time, and so that's just not as important anymore. And reliability and things like that, polishing the corners and making all the commands easier to use has, you know, taken over in terms of priority. So that's, you know, those are not features that you write home about, but things like the, you know, the MDT space balancing, right? It just works under the cover. You don't really see, you know, much difference except that D&E 1 and 2, which took, you know, 10 years to develop, you know, it works now without a PhD.
Well, the reason I'm asking is that, I mean, you know, I think everyone in this country lives, this room lives and breathes Luster in one way or another. Unfortunately, I'm seeing some decisions from upper management in not just our company and others that keeps claiming that Lustre is running out of steam, we need to come up with something new. But that is not what you think in this case.
No. I mean, if you look at the performance numbers, right, I mean, some, competing products, right, they claim, oh, it was engineered from the ground up for flash and blah, 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 right, and we don't have the legacy, encumbrance of disk storage. But if you look at, QLC flash, it's really like a RAID device. I mean, it needs big aligned writes to get the best performance. That's like RAID. And, if you look at the performance per unit capacity, Lustre does way better than many of those competing products, even though they're, engineered from the ground up. It's just that they're written badly and, didn't, I mean, it's true with, I call it lazy programming today, where, you have this, Python multi-layer framework, and the developer resources are the expensive thing, and the hardware resources are the inexpensive thing. And so the lazy programmer can get something done just by scaling it out to many nodes, and you don't have the focus on what, making the most efficient usage of the individual components, right? And, Lustre has grown up, in the day when I/O was, expensive and you optimized for it. Right, and so I think we still have all of that benefit. And I presented in another presentation a few years ago the scaling of Lustre over time, and we've actually had a super linear scaling above the speed of the hardware, which is growing exponentially, whatever, 1.2 times a year, and Lustre performance has been growing at 1.3 times a year because we keep on making more and more efficient usage of the hardware over time. And so, is Vim running out of steam, or GCC or whatever, right? It's just because it's not getting tons of feature doesn't mean that it doesn't work. It's actually sort of better to consider that it's not getting, tons of things crammed in Lustre 2.4. If you see Peter Jones's slide and the number of lines of code that went into that release, right? And granted, ZFS and D&E both went in at the same time. But that led to, a lot of hardship in terms of stability, right? So we're still seeing, interesting features going into Lustre. It's just not as high a priority as it used to be.
Thank you.
Right, so our next speaker is Marc-André Peuf. He's a PhD candidate at Johannesburg Gutenberg University, Mainz. His master's thesis was in cooperation with IBM Research about analyzing file create performance in GPFS parallel file system. His studies about studies with IBM Research further investigates tracing techniques in parallel file systems. He's the maintainer of GeckoFS distributed burst buffer file system in collaboration with Barcelona Supercomputing Center. Overall, his research interests focus on file system storage, object store, and system analytics.
Okay. Thank you for the introduction, and also thank you for the organizers of this wonderful lab workshop here. Again, my name is Marc Peuf. I'm a PhD student at the University in Mainz, and I'm in the group of André Brinkmann. And we have been involved in the past in a number of different research things with Lustre, for example, the token bucket filter, but also LPCC. And today I want to talk also a little bit of a different talk, where we talk about what we're currently doing, where our research is going at the moment. And at this point, we're looking into concurrent write support for the persistent client caching that we have. And yeah, let's go. So first of all, I want to do a little bit of an outline because we're touching on a number of different topics. Firstly, what we want to do and what we have been doing in the past years is we looked into ad hoc storage system. This is where the GeckoFS that you just heard in the introduction comes into play. And I want to present this as an example and how we can potentially use this in the persistent client cache and Lustre that's based on the HSM. Then I want to also talk about the limitations that both the ad hoc storage systems have on a broad, in a general sense, and then what the PCC limitations have and how we can combine all of these together. So if we look at the cost of using the parallel file system, this is something that we have seen at the Barcelona Supercomputer Center. This is in this case not a Lustre but a GPFS, but we've also seen this in Mainz where we have a Lustre. Is basically that if we would run the same workload over a week at different points in time, we have different performance that the user sees, and it can be in orders of magnitude difference. So we have a huge variety in I/O performance, and of course the applications suffer from the PFS load. They don't really know what performance they're going to get and how much time they should allocate for their job. So of course, the other thing, and we've heard this also for the persistent client cache, is that we have these node local storage SSDs available on the nodes, but they're not really used by the applications themselves. So one of the things, of course, here is in the motivation that we want to exploit the whole I/O stack, and we want to reduce the data movement. For example, if we have only data that is, only used within a job but not later written out to the storage system, or is not supposed to written out to the storage system, then it doesn't make sense to write it down to the parallel file system. So in the end, improve data locality and do work where the data actually lives. So what we have nowadays is that we have this situation where the applications are running directly on the parallel file system and we have uncoordinated access. So every application is kind of doing what they want. Node local storage is typically ignored, and we have these variability that you've seen earlier in the slides. So what we want to do is we want to actually have that all of the applications are basically only running on the node local storage, and then in the end we can, in a more sequential sense, write the data back that is actually or should be persisted on the parallel file system. And if we have the appropriate schedulers here, we can have this, or we can do this in a way that is most suited to the parallel file systems. So if we have a lot of random I/O, have a lot of file creations, these can then be absorbed by the node local storage, and therefore we have reduced the parallel file system contention, reduced the variability, and at the same time for applications who actually need to use the parallel file system for whatever reason, they also benefit from that because some of the load is taken away from it. So one of the things that we want to do, and this is where the ad hoc storage system come into play, we want to basically use the SSDs that are available there and put them together so we can use the performance and the capacities of these SSDs together, and in the end, hopefully achieve linear scaling the more nodes we have. And here I want to talk a little bit about the research that we have been doing and that is still ongoing, which is the GeckoFS burst buffer file system as an example of what we want to use later. But again, this is just a stand-in and could be any ad hoc file system like BGFS beyond and so on. So for GeckoFS, the core challenges that we wanted to do, we wanted to have a file system which is of course very fast, because if it's not fast, then there's no reason to use it, right? So we changed a little bit about how the file system internally behaves so that we have no central control components, we have no global locking, and therefore can achieve the linear scaling with the number of nodes. The next part is, if such a ad hoc storage system is deployed, it is also very important that this happens very fast. You cannot spend minutes at the beginning of a job to just start this ad hoc storage system, because it's first of all very expensive. So for GeckoFS, for example, we can do a deployment in about 5 seconds on 512 nodes. The third part is we wanted it to be completely in user space. So that means the user can do whatever they want. They can start up the file system, they can use it, and there's no administrative support necessary. So, and the admins don't even need to know about it, except that now suddenly the node local storage is used. And finally, all the storage that is available to the user. It could be memory, it could be the SSDs that are available on the nodes should be used by that file system. And also a fast network fabric should be used efficiently with RDMA and everything that comes with it for Omnipath and InfiniBand. So to give you a quick look on the architecture that we have built, this is important later to understand how that works. So basically what we have here is that the application is using just normally the libc library to use all their I.O. calls, and then what we do, we intercept these I.O. calls with LD preload. But not the normal LD preload, but we do it with a system call interception library from Intel so that we only really intercept the system calls and not FWrite, for example. And then what we're basically doing, then we are in this user space library, and then we just distribute it across all servers. And we do this with a high-performing RPC framework that is created by the Argonne National Labs. That's called Mercury. And on the server end, that is called the daemon here. We store the metadata in a RocksDB, which is also stored on a local storage system, on a local file system. It could be ext4 or XFS or any other, where also then in the end the data is stored. And of course, before the GeckoFS can be used, you would need to stage in and out the data at the beginning and the end of the job. So how does that look like? If we look at the performance that we had in the beginning, where we looked at the I.O. variability of GPFS, and this is basically the same plot, now with GeckoFS included here, and of course, because there's no variability, there's no congestion on the nodes, you have very linear scaling, and we did this up until 512 nodes. We're showing here the 32 nodes, up to 32 nodes, and it's very predictable for the user. We can also look at the metadata performance. In this case, apologies, in the top right, it shouldn't say GeckoFS versus BGFS, but versus Lustre. This is at our Morgan II supercomputer at the University in Mainz. And in this case, we wanted to look at the benefits that such an ad hoc storage system has compared to the parallel file system. And in this case, we weakly scaled this GeckoFS file system with 16 processes per node, with 100,000 files per process, simply with MD test, up to 512 nodes. So in the end, we have over 800 million files, and we get close to 50 million creates per second. We also compared this here with Lustre, but of course, in this case, it is a smaller installation for this specific file system, so we only had a single MDS and a single MDT with just a couple of hard disks in the back, and there, of course, it plateaus off very, very quickly. For the GeckoFS, we ranked fourth in the IO 500 10-node challenge in Supercomputing 19. Nowadays, there's a different file system at the top spots called MadFS, but it's very much inspired by GeckoFS, kind of recoded in Rust, but the algorithms are very much the same, and they're using a different network library, which is very interesting for us because it shows that our architecture also works on much, much faster clusters that we have available at the university. So now what is the problem? Why don't everyone uses these file systems? Now, these file systems are not transparent to the user, and they really require user interaction, not only with starting and stopping the file system. You could achieve this very simply with Slurm scripts, Prolog and Epilog, but you would also need to stage the data in. And in that sense, there's currently a EuroHPC project running called Admire, where we want to specifically look into this. This is from a collaboration with 14 European partners from Spain all the way to Poland, where it's basically about adaptive multi-tier data management with a focus on computational and I/O malleability. That means, for example, an ad hoc storage system can be on a number of nodes, and while the application is running, we just expand the number of I/O nodes. And at the core of this project architecture, we use ad hoc storage system, not just GeckoFS, it's also ad hoc storage system from the University in Madrid as well, but also from the Barcelona Supercomputing Center. Since DDN and the University of Mainz is part of this project, there's also an idea of actually combining the benefits that the persistent client cache in Lustre has with the ad hoc file system. And now I want to go a little bit back about what the HSM actually brings and what PCC actually brings for those who are not aware. But in the end, the takeaway here is it's somewhat difficult to actually use them in real life. So for the hierarchical storage management, I think this figure floats around for over 10 years now, but basically it is a framework for tiered storage, typically archiving, where we can move the data to text, for example, while the metadata still resides in Lustre. And if we have an I/O operation that would happen on the file that is currently on the tape, then we would automatically trigger a flashback. So it's very user transparent. There are a number of components here, the MDS coordinator, the client agent, and the POSIX copy tool that we heard earlier today that kind of coordinates these archiving and restore operations. Now this HSM is then used for the Lustre persistent client cache, and this motivation and goals for LPCC is very similar to what we have with the ad hoc storage systems. Node local storage isn't used by anyone, by the users that is. And the goal is, of course, to increase the I/O performance and decrease the I/O interference. But in this case, because it's directly working with Lustre, it is transparently included. So the drawback that we have in the ad hoc storage system is here solved. For the features, LPCC can maintain a global namespace, and we have basically two caching modes. One is read-write, and one is read-only. At the moment, read-write cache in Lustre for LPC is only for a single client, and read-only is actually for multiple clients. So how this looks like from the architecture, this is from the paper that we worked on together with DDM and OneCloud here. Is basically you have the MDS and the MDT with a coordinator where the file 1 to 3 here is actually stored on the node local storage, and then the actual data is no longer there on the OSTs, and the client can directly use the node local storage system here. And in this case, the LPCC has actually an HSM copy tool and agent running to archive and restore the data. If we look at the performance here, this is also from the paper where different workloads were run. One is just simply with IOR, the other is an HPC benchmark, HACC, where Lustre and PCC is compared. And of course, based on the installation that they were having here, Lustre plateaus at some point, but the PCC implementation, of course, linearly scales with the number of nodes because they are only using the storage and has no interference. So what are the limitations then? LPCC offers caching only in the context of a single node. That means for read-write that if multiple nodes want to cache the same resource, that is not possible, and then we have a fallback to the normal Lustre way of working directly on the parallel file system. So there's no parallel I/O from many nodes possible. For read-only, multiple nodes can cache the same resource if they're opened in read-only mode, but it leads to redundant data. It's not that the data is distributed across all nodes, they're actually duplicated. And if hundreds of nodes are doing that, in certain workloads, that can then, of course, also lead to I/O overhead here. And finally, if you have a file that is bigger than the node local storage here, the SSD, then of course you cannot save it because it simply doesn't fit, and the I/O performance is also restricted to the storage. For metadata, it is a little bit more difficult. As far as we know, you can create a file there, but you still have to talk to the metadata server to create it, so you have a bottleneck here for creation, but then the consecutive stat operations, for example, are cached. But in general, ad hoc storage systems, and now we come back here, can offer a solution to this limitation because we already have these right striping of having linear scaling for metadata and data workloads, regarded if you have a shared file or a file per process, random or sequential I/O. So when we started this, so the naive coupling approach is just if we look at that, by the applications using the Lustre client and PCCs using the node local file system, we could just replace the node local file system with a distributed ad hoc storage system. That would be very nice, except that this is a huge coding overhead, right? Because you need to change many, many things. The logic that we have for read-write and read-only caching in PCC must be largely rebuilt. There's also the question, what would happen if a remote node is accessing this data that is currently on an ad hoc file system? How do they get the connection, and so on? There might be little benefit for metadata workloads, specifically for creation of files. And then, of course, this all must be tested. So there's just in general a lot of coding overhead and complexity in here. There's also the concern that this is maybe a little bit too specific for a general Lustre ad hoc file system approach. We might be able to get it to work for a specific file system like BGFS or GeckoFS, but not for all. So overall, this is not a satisfactory solution. So our proposal, and again, this is very much work in progress. We haven't tested this or really built this yet. But what we're currently thinking, this is why we're eager to hear your feedback, is instead we want to build on the existing Lustre HSM mechanisms, do somewhat similar to LPCC, maybe also include some of the LPCC's components, but largely avoid extensive Lustre modifications so that the solution can more or less stand on its own. It should be semi-transparent, not as difficult to use as ad hoc storage systems, but there's also some user interaction involved if you use LPCC, and this would be kind of the same here. And then we can also include something that we've learned when building GeckoFS is how we can use the interception layer here. And in the end, the goal is, of course, the compatibility with any distributed ad hoc file system. So how would that look like? If you have a compute node with a Lustre client and a distributed ad hoc file system running, this is how it would look like today. And then you also have this interposition decision library here. And the purpose of this library is basically just to say, well, should this specific file be cached, then it would go to the ad hoc file system. If it's not cached, then it would be just a fallback to Lustre. So how that would work, as a proof of concept, what we're trying to build, is that first of all, a user or a Slurm Prolog script would register the HSM, normally as you would also do it in LPCC, without release. So we do not want to actually delete the files that are currently on the OSTs, simply because you have more nodes involved for a distributed ad hoc file system. And if one node fails, you already lose your data. This is kind of the purpose of the ad hoc file system. We don't really have the persistency here, but there should always be the fallback here for Lustre. The next part is that then the application will use LD preload again and uses this interposition decision library, which already knows what files should be cached. And there can be some communication between Lustre and this decision library here. And then once the application is doing an I/O request, like a write on a specific path, this decision library would then decide, should I forward this to the normal Lustre or to the ad hoc storage system? For staging data, for now we are looking into that the distributed ad hoc storage system has kind of the responsibility of getting the data lazily when it is needed. But we also would like to include some of the work that has already been done in LPCC, like prefetching, use of the copy tool or the policy monitor. And then finally, of course, if there's a conflicting access happening, similar to what LPCC already has, then the data should be flushed back immediately to Lustre. And why is this the case? Simply, we do not want to have this ad hoc storage system for the complete compute cluster. We want it, for now, basically only for a specific job or at least user, right? So this flashback still needs to happen. So if possible, then the next steps after this could be a future kernel integration. So of course, we already know with GeckoFS, these interposition libraries can cause issues. And we've seen this already for most applications that works fine. But there are some issues here, so a kernel-based solution is always preferred, also for transparency for the user, of course. So our idea is to move this decision library to the kernel as a shim layer or a pseudo file system in between the VFS and Lustre, which would look like this. So it's basically the same idea, which is no longer in user space, but now in the kernel, in which then this shim layer decides if it should forward the request to an ad hoc file system that is in the kernel, or any other. Could be GeckoFS, could be BurstFS that is developed in the US, or Hercules that is developed in Madrid, for example. Okay, so to conclude, we have basically two solutions here. We have LPCC, and the drawbacks here is that we do not really have a concurrent write caching across multiple nodes. The ad hoc storage system provide that, and on the flip side, the ad hoc storage systems solve this distributed concurrent write support, but they are not really easy to use and they're not transparent. So the idea is to combine them and hopefully get a better result here. And the discussion here would be, of course, and I'm happy to talk to you in the break about this as well, is what pitfalls do you expect here to happen, because there's a lot of things that obviously can go wrong. What would your requirements be to use such a systems, also from an administrative perspective, and what are the typical use cases you see? There are already a bunch of use cases for ad hoc storage system, of course. It could be deep learning applications, checkpointing applications, and so on. And that is this. Thank you very much. And now questions.
Question, James.
Yes.
First question is, Git repo for this?
Yeah, for GeckoFS?
Yes, for all this work. Do you have it available?
Okay, so again, we have GeckoFS available. It doesn't seem to be the last slide deck, but yes, we have a Git repo available for the work that we want to do here. We don't have anything public yet. We have very much just started the work. We very much know already how this interposition library would work, but the communication between the Lustre client and the distributed ad hoc storage system about how to stage data around, we're not finished yet.
Okay.
Yeah.
Second question is, for the shim layer, why not Fuse?
Well, it is in a sense very similar to Fuse, but at the same time, you have to, well, we had this discussion a couple of times in the end. And we also know that if we, for example, have a GeckoFS with Fuse, it would be very slow, simply because of the number of context switches, the back and forth between kernel files, right? So the idea is what we want to do in the shim layer is a little bit different than what Fuse does. First of all, we don't need Fuse if we have a kernel-based file system like BGFS. We can just call it directly. But if you have something like a user-space file system, we are looking at another way how this could communicate with user space. It can use the Fuse device, but it could be a little bit different. So we're not yet finished on the decision. If some parts of Fuse we could use, but we are quite sure that we will not use Fuse simply because the other user space file system would need to include that as well. So we would like to keep them the way they are. Okay.
Another question? Perhaps online? No question online? Okay, thank you. So it's time for the break. We have a break of 30 minutes. So we have to come back at 3:45. Thank you. So we are at the end of the Thursday afternoon. So welcome to our next speaker, Sébastien.
So Sebastian's been working at CA for 3 years in the HPC division. He's currently a software developer working on Robinhood and Phobos. He also leads the data science team to use machine learning algorithms to better understand and manage computation clusters.
Thanks, Gaël. Thanks, Guillaume. Hello to everyone. So we are here to talk about a dinosaur for Lustre, Robinhood, and make a little progress report about the fourth version of Robinhood. So no news, good news, or bad news? Well, yes, good news. The last update at LAD was 2 years ago, but reassure yourselves, Robinhood is still in development, still alive by the CA and also former members of the team. And developments can be followed on Geritam and GitHub, following this link here, for instance. And also, this is not dead because we need to have it soon in production on our clusters, because we need to scale up. And the third version, as Torben said earlier, is too slow to encounter our performance requirements. So, just to remind you, what is the main focus of Robinhood? Its goal is to provide efficient and easy ways to replicate and query any file system's metadata. And I accentuate the any file system because the previous versions were only specialized on Lustre, and this is not the case anymore. As said in this slide here, because we have multiple reasons to build a new version of Robinhood. So comparing both third and fourth version, we need first to scale up, to be faster, to have better performances. And for this, we chose to not use anymore SQL paradigm with MariaDB, but going to a NoSQL paradigm with MongoDB, because it scales better. Also, we work on code genericity because the third version was a huge software which was specialized for Lustre file systems only, and our goal is to consider a very large set of backends. So we will try to have generic tools, each tool having a lone feature and can be used using any backend available. Also, we will try to include it into Linux repositories, and having an expert system with Lustre is not easy to include it, so we will better have a library with different features and applications. And last but not least here, it's about code refactoring. The third version was an heavy code, really heavy code, caused by Lustre behavior evolution, and do an update of this version was complicated. Maybe you don't know, but the number of unit tests for Robinhood was incredible. The fourth version, we will start from a clean design and also why to better correspond to current file systems. So here I will present some things that were done in the past, that are currently done, and we expect for the future, of what Robinhood v4 is composed of. So Robinhood is first, as you can see in the center of the slide here, of a core library which will have the goal to communicate with different backends. So here we have a first POSIX backend, in which it will retrieve the metadata of the files that are on it, okay? And we also have a Mongo backend to store the metadata that were retrieved from the POSIX one and also query them. That's why you have an arrow with two directions for Mongo, but only one for POSIX, as we cannot fetch yet the metadata directly for POSIX file systems. And we have also two tools that were already presented in previous lab presentation. RBHFind to query and filter all the files you have on your mirrored backend using different filters as the size of the files, who made them, at which time, and also RBH Sync tool here to synchronize a backend into another, and here to retrieve all the metadata of the POSIX backend to store them in the Mongo one. In development, we had two new tools that we will present a bit later. The first one is RBHL Find, which consists in an overload of the RBH Find to fetch files depending on some Lustre attributes. And we have also RBHFS events to retrieve events from the file system. That can be Lustre change logs, but also maybe fan notify events or other things to update the Mongo database. And also we have on the right part the Lustre backend that we can now retrieve metadata from. Also only in a read access. And on future site, we have at least a need for having an RBH report tool that will be used to retrieve some generic statistics of the file system, as how many files I got in it, maybe having some statistics grouped by user groups or projects. So if I go back in the time, back to 2020, we presented to you two main features that were developed in the past for the year 2020. The first one is the support of custom extended attributes, which means that we can attach to every entry a key value attributes, like here you can see the path, the name of the file, and also as we made for the Lustre attribute using those extended attributes, and also presenting the conversion between Robinhood file system events and YAML to easily pass the information from I got file system events, I need to enrich them with a Lustre enricher, for instance, to retrieve some statics attributes, or new Lustre attributes also, and then update them on the Mongo backend. And also, because this conversion is already developed, the fact that we need to handle a new backend only need to convert specific logs, so for instance, changelog Lustre, into file system events to be directly digested by the enricher and then the upsert into the Mongo database. So now I will talk about three features that we worked on this last year, presenting for each of one a small demonstration. Not really crazy about that, but just to show you how it works. The first one is additions to RBH Find. So we added some filter options, like the size option, permissions, but also having a filter on extended attributes. And we can easily add new filters depending on what we need, what you need, to fetch metadata and define data placement policies. Also, we added the sort and reverse sort options to, for instance, retrieve all the files depending on their size, the huge files first, and adding some actions as ls, fprint, fprint0, and fprint and fls. But those actions are already defined in Find, so you know what they deals with. So, a small demonstration, so sorry for the size. We have to the left side here the first command on line 1, which consists in synchronizing a POSIX file system, which is the mount point of Lustre, into a Mongo database. And we can see that using RBH Find, we can select all the files that were in it and sorting them by name, with big, huge, and small, or also sorting them by size, small, big, and huge. Okay, you need to be confident of this. If you have some doubts, you can still check the ls command, the ls option here in RBH Find on the right side, where we can, yes, you can see that, okay. You can list and first the files, so we have small, big, and huge that are effectively small here, yeah, the size here. And then if we sort them by size, we have the huger files first, then the big and the small. We can also do, so this was the reverse sort. We have the normal sort here, beginning with the smaller file. And then we can also sort them by name. All right. So the second point is the Lustre backend, as presented earlier when presenting the different components of Robinhood. Lustre is a file system that we use in our clusters. And so we need to store relevant information of Lustre in the Mirror backend to determine the data placement policies that we need, such as the FID, the file layout, the OST, and also HSM state, for instance. All those information are retrieved during the synchronization between the Lustre backend and the Mongo backend, and they are converted to namespace attributes, aka the custom extended attributes I talked earlier, or the entries stored in Mongo backend, the database backend. And then the need was to filter all those entries using those information. And why we needed to overload RBH find to a RBH Lustre find is because we didn't want to have some options that are dedicated to a backend into our generic tool. So here, another example. So I created a set of directories, and in each directory, some files. And I set for the 12 file of some directories an HSM attribute to archive. The same thing with the 11th file of those directories with a no release tag this time. And then I did the synchronization. Okay, so we can print the head of RBH find result. Also note that we did not use the POSIX backend anymore, but the Lustre one to effectively retrieve the Lustre attributes. And so we have some directories and files. Here we can see with the Mongo query that there is Lustre attributes in each document. So here I printed it blue. So the first one, some information about Lustre here, the love, some, etc. And also below the FID, HSM state, flags, some things about the stripe. Here are no stripes because we didn't put one. And also the OST, which is the number 0 here. And if I try to use our RBH find tool overloaded for Lustre, RBH-L find, we can then use an OST filter to sort all the files that are with suffix, an even suffix. If I use the OST1 filter, I got all the odd suffixes here. Also, I can, using the FID of the file, use it in a query to retrieve it. Okay. And to finish, we got here a query using the HSM state, and we can see that for archived and no release, I got first the 12th files, and in the other, the 11th file. The last point is about Lustre changelog reader, because without it, it will be difficult to have great performances on our clusters. So, as said earlier, the only point we have to do is to convert changelog events into RBH-FS events. So we are currently on this development, and first events are processed, so I can show you some results on that. Others are, of course, following. And we are still thinking about the right moment to acknowledge the events. Why? Because we can wait that the Mongo backend is updated before acknowledge the events, but maybe just having them stored in a temporary file, in temporary YAML file, for instance, is sufficient enough, and we don't need to wait the whole upset to acknowledge some events. That's something we have currently in discussion, and we will try soon to answer it right. So, a small demonstration also. I created a null file in the Lustre mount point. I defined that I need to register a client for the changelogs, and then I change the access time of old and create new. I can see using LFS changelog command on the metadata name that we have 4 different events. The 2 first events are for the modification of the access time, meaning we have a ctime event and then a close. And the 3rd and the 4th are for the creation of the new file. Okay, and if I use the RBHFS events saying that I need to enrich it, meaning to fetch statics, attributes, and other things that are not stored in the changelog event into the mount point, checking the client Lustre MDT 0000 and printing it in the standard output, I will have first here the upsert with the change of ctime and haytime. Then here the close event that is converted into an haytime modification. Here the big one is because of the creation file, because we need to retrieve some information about the parent, in which directory it is, its name, its path, starting from the mount point, its FID, and some statics here. Not everything is written in it because it's too big. And then we have also the close event here that was translated with the haytime. So then what's next? What's for the next year? First, I need to say that additionally to Lustre, we also develop a non-Lustre related backend for a European project called IOC, which have the goal to build an I/O storage software stack for European clusters, using Cortex Motor and Phobos as object store and not only as file store, meaning that we will have really a generic backend for Robinhood that can treat both file and object stores. Also, as you saw in the previous slide, the last demonstration, we will have to work on FS event deduplication to avoid having multiple events concerning the same file. Just merge them and saying that you need to retrieve the last attributes that are modified. And also, as I said, as a starting point, we will need to have RBH v4 ready for clusters. So pre-production tests will begin really soon on our systems to have Robinhood in production during 2023. Just to remind you, the repositories are available on GitHub. Here for the 5 tools that I described in this presentation. This is Torque, LibRobinhood, RBH Fine Lustre, RBH Sync, and RBH FS events. And reviews and codes are welcomed. Thank you.
Thank you. Any questions?
Hi. Maybe you mentioned something about it, but if I understand it correctly, Robinhood has some sort of direct hook into Lustre because it can consume the transaction logs. But do you have something similar for like BGFS or GPFS? Or do you need to use this Robinhood find?
Not yet, because we focus on what we need on our clusters, but it is possible to add a backend for GPFS or BGFS, and then use the default tools, the generic tools that we have, and if you need other filters or other options, make your overload tool, and you will be able to use it.
Another question? There is one question online, Thomas. The network?
Yeah.
Okay.
The online question will be read.
Okay, what is the largest file system in terms of number of object files that you have tested playing with before?
I can't give a correct answer to this because we didn't have a real large stress test for our version. It will be something that we will try soon. We have some synchronizations that were already made in one of our clusters, but there are some optimizations that were not taken into account, so I cannot give a correct answer for that. But you can refer to previous presentation of Robinhood V4 that were made by Quentin Bouget in LAD 2019, I think, where he presents some performance metrics and maybe can answer your question.
Okay, anyone? No one online? Okay. Thank you, Sébastien.
Thanks.
Okay, our next speaker is Sébastien Buisson.
Hello again. So this is a presentation of the hot pulse feature. So I am not a hot pulse expert. Alex Zuravlev, who is our hot pulse expert, could not make it to Paris and attend LAD, so I am doing this presentation. And so may you have any questions, I can try to answer. There is also Andreas Dilger in the room, so at the end of the presentation, we will try to answer questions for you. There will be 2 quizzes in this presentation. No, I'm just kidding. No quiz, you can relax. And yeah, so let's get started. So what are hot pulse? Hot pulse is an automatic tiering system for Lustre. This is a trendy topic these days. It is managing data placement between standard and fast Lustre components. This is part of the DDN Exascaler product, so I'm not going to detail every feature in the DDN Exascaler product. We are going to focus only on hot pulse and show you how it makes use of different interesting Lustre features. Hot pulse automatically manages flash OST pulse. It allows workloads to be transparently moved to utilize flash tiers. There is no special programming modifications required for your applications to use that. So the purpose is to reduce overall disk storage system load by offloading high I/O demanding applications and processes to flash tiers. It also manages flash tiers to avoid running out of space, and it automatically spills over to spill pulse to disk if needed. So there is this diagram to give a rough idea of how hot pulse work. So basically, your application initially lands on your flash tier, and then data is mirrored, is moved to disk tiers. So you can imagine that your application is handling files that are stored, that are residing on your flash tier, and there are internal scanners on MDT and OST devices that are analyzing file accesses and then mirroring those files to disk tiers in the backend and in the background. Sorry, and you can obviously do the other way around and on demand mirror back your files from the disk pool to the flash pool. So hot pulse basically relies on 2 main Lustre features. The first one is progress file layout. And the second one is file level redundancy. So we are using PFL to write files, initially write files to flash pools, given that it's possible that you can configure PFL to write very large files directly to your disk pool. And then Hot Pulse relies on two tools. The first one is called Lamigo. It runs on MDS side, and its role is to actively mirror new files. So there is one Lamigo instance per MDT. Lamigo starts by scanning the MDT devices, and then it consumes Lustre changelog. So at this point, it's a changelog consumer to follow which files are new and which files are modified. And it waits for files to be inactive, and then it triggers file mirroring, basically like you would do with LFS mirror commands, to mirror files from the flash pool to the disk pool. The other tool on which Hot Pulse relies is called LPurge, and its role is to monitor flash OSTs to purge old files. So there are one LPurge instance per flash OST. It periodically scans your OST flash devices for unused files. And so this scan is made at a very low level so that it's cheap and efficient at the same time. The purpose is to maintain a list of the oldest files on those pools, and then to purge those pools because they are precious. They have limited space but high bandwidth and IOPS capacity. So the purpose is to purge those files when space is needed, but it's also possible to quickly release space on demand. So we've been working on newer enhancements to the Hot Pulse feature. The first one is called Active I/O Tracking. So basically you have this capability inside Lustre for OSTs to be able to log every access that is being done. And it's an in-memory circular buffer of all I/O accesses as seen by the OSTs. And Lamigo is able to collect and aggregate those I/O logs per file. So only a fraction of data is read by the server, and only a list of most frequently accessed files is updated. So we are building this history table of files that are associated with a hit, and basically this hit would increase if a file is accessed frequently, and if the file is left untouched, then the hit will slowly decrease. So this is useful for a number of optimizations. For instance, if you have a file that is on your flash pool and that is hot, then there is no point in trying to and spending time mirroring this file to the disk pool. That would be a waste of resources because we know that this file is actively being accessed, so it is kept on the flash pool only and not mirrored. And conversely, you can have a file that has been mirrored to your disk pool, and then for any reason it becomes hotter. And then in this case, you could imagine that it would be nice, in order to improve the application's performance, to automatically mirror back this file to your flash pool. And so this is a newer feature. It's still disabled, and because there are still some work needed on the fine-tuning and find the best, let's say, parameters to decide which files to mirror back automatically. The other new feature is called pool spilling. So it means that for every OST pool, you can define a spill pool. And the use case is if you have a flash that is filling up faster than it drains, then you would want to avoid creating new files on this flash pool. So if you are defining PFL so that your new files are created on the flash pool, and then this flash pool becomes full, then you would get space errors for applications that are trying to create new files. So the spill pool mechanism avoids this problem by detecting that the initial pool is full, and then automatically and directly creates the new file on the spill pool. So it releases pressure on the full pool, and at the same time, it throttles down write speed, but this is to avoid running out of space, obviously. This can be configured with two tuning parameters. The first one is to define which spill pool you want to use for a given pool. And the second one is the threshold percentage. So it means at which point you want to get full before spinning over to a different pool. And you can chain spill pools so that we support up to 10 spill pools and not an infinite number to avoid infinite loops. Okay. Another enhancement that is beneficial for Lamigo is to support rules. So Lamigo is the tool that automatically mirrors files from your flash pool to your disk pool, and it does that for every file. There is no distinction, and policies let you refine this behavior, so you can define filters which will decide which files will be actually mirrored. And you can define filters on a number of attributes, of course POSIX attributes like file size, timestamps, owners, file names, extensions, also extended attributes like HSM and LSOM, so internal Lustre attributes, and any regular extended attribute in the name value format. A number of improvements have also been made to improve file mirroring. Initially, it was not possible for Lamigo to run on a pre-existing file system. So now Lamigo can run on such a system, so it's very useful if you have an already existing file system and then you decide to enable hot pools. So in this case, there will be a scan of the whole metadata devices. This is required because in such a case, there are no pre-existing changelog records for the logs that were already there on the file system. And it's also useful if you have lost some changelog records. It's possible because changelog are consuming space on your MDT devices, right? So you could run out of space, and then that would mean clearing some oldest changelog records, or there could be errors in the changelogs. So thanks to this scanning capability, it's possible to use Lamigo on already existing file systems. And there is also the name changelog user and a per user changelog mask that is new to Lustre, and it simplifies automatic registration and minimizes overhead at the same time. Another enhancement is the possibility to know the rotational status of a given pool. So it means, are you defining a pool that that consists in disks or in NVMEs, in SSDs? So it's possible for Lustre to report the status. If you define a pool, then you can have access to the information, whether it's based on rotational or non-rotational storage. And more importantly, the client would automatically prefer the pools that are non-rotational. Of course, it doesn't mean that, so you can still use the prefer flag on your pools, but this feature avoids you to have to set this prefer flag on every OST pool. Okay, so I just want to present a small testing we've made. This is on this configuration. We have obviously one flash pool on NVMe and one disk pool that is using rotational disks. If we write directly to the NVMe storage at the backend level, we have a performance of around 15 gigabytes per second. And if we write directly to the disk storage, we have, so rotational storage, we have around 10 gigabytes per second. And the test consists in running IOR in a loop from 2 clients. And here's what happens on Lustre. So on the left-hand side, you have what is called the performance pool. So this is the flash pool. And on the right-hand side, you have the capacity pool. So it's larger and it's made of disk pools, rotational pool. And you can see the write pikes in yellow that correspond to IOR running in a loop. And if you have a closer look, you can see smaller green peaks. So these are read. This is a read activity. Obviously, it's not made by the application itself. This is the result of Lamigo activity, that is analyzing the files being accessed and mirroring in the background those files from the flash pool to the disk pool. So you can see the corresponding write peaks on the capacity pool on the left, on the right. And so this is happening in the background during the time the application runs. And at the bottom, you can see that capacity is filling up progressively on the flash pool and on the disk pool. So what are the use cases we see for hot pools? The first use case is very useful in HPC applications. So I'm talking about the applications that are designed according to the checkpoint restart model. In this model, your application is going to compute for a certain amount of time that is usually fixed. After this time, the application will proceed to checkpoint, which consists basically in flushing its memory down to disk. And after that, it will resume computation for the next cycle. And obviously, while the application is checkpointing, it is not computing, so it could be considered a waste of resources regarding the computation resource in the cluster. So the purpose is to reduce as much as possible the time taken by the checkpoint step. So if you consider this, you can imagine that the application that is going to checkpoint will do on the flash pool, so as quickly as possible. And then once computation resumes in the background, while the file system is not used by the application, then hot pools will proceed to mirroring to the disk pool in order to release pressure on the flash pool. The other use case is that with this feature, we have virtually infinite flash capacity. If you consider that an application uses files for some time and then they are barely accessed again, it means that your application will always use files, create new files and use them when they are on the flash pool. And then once they are moved, they are mirrored, to the disk pool, they are barely accessed. And the third use case is obviously backup, because this mirroring capability means we are making multiple copies of the same files on more economical storage. So that can be seen as a backup capability. So at the beginning of this presentation, I told you that hot pools is a DDN exascalar specific feature, but it relies on a number of Lustre features that are already available in the code. For instance, the pool spilling feature is available from Lustre 2.15, as well as the name changelog and user and per user mask. Regarding rotational status, from Lustre 2.13, OST pools are already reporting their rotational status. And in Lustre 2.15 was introduced, the capability for Lustre clients to automatically prefer the non-rotational pools. And the IO access log capability has been here from Lustre 2.14. So this is the ability for OSTs to log every I/O accesses that are carried out. And that's all for this presentation. Sorry again, no quiz. Do you have any questions?
Thank you, Sébastien. Questions for Sébastien?
Can you pin the project on the hot pools, for example?
Sorry? You want to see that slide?
No, my question is, for example, we have a lot of different projects.
Yep.
Can you pin specific projects on the hot pool?
You mean so filter depending on the project ID?
Yes.
I guess so. Yeah.
Thanks.
The first line.
There's also a specific command to pin individual files.
Okay.
Well,
Maybe
one
you
second,
can give
Louis.
the mic to Andreas.
So yeah, the example here, it does filter out specific project IDs from being purged from the hot pool, right? So you can do it as a general policy, but there's also a command LFS pin that, oh no, that's for PCC, never mind. Sorry. There's the capability that we might write in the future.
I guess using the file name, filter, you can always end up achieving what you suggest.
Another question.
LPurge was mentioned as the tool to purge old data from the flash pool, but could the same tool also be used for the disk pools to get rid of data which hasn't been accessed for, let's say, a year?
Yeah, I don't see any good reason why not to do that, but I cannot see any good reason why to use this tool. I don't know. If maybe, yeah, if you need something efficient, why not?
Yeah, my question is basically, is it super specialized to just work on Flash, or is it so generic that you can use it on any pool you want?
Well, maybe Andreas.
Yeah, no, the policies are only based on the pool names. It doesn't know anything about, this is Flash per se, yeah. Right? But at the same time, the only thing that LPurge does is it just releases the mirror from the Flash pool and keeps the mirror on the disk pool. It doesn't actually delete the files or anything. So you would probably just be better off having a tool that does a find or whatever and then deletes the files, right? I don't personally like, having automated tools delete files. So, that's something that usually is done, by multi-step process, sending, confirmation to users and things like that.
Again?
Yep, it's me again. So have you heard about production experiences from using hot pools? You mentioned that there are a few features which are still quite fresh. Have you heard any experiences from the field?
I don't have personally. I don't know
Somebody
if
from
Andreas
DDN?
has some feedback that can be shared.
Yeah, so there's, I wouldn't know. I mean, there's 20 or 30 sites that are using hot pools at least. And so it's generally, in pretty good shape now. Migration from disk back to flash, that's the main newish feature. I haven't heard particularly bad stories about it. It's hard to know for sure. I think many pools are set up so that, the main working set stays on flash. And if they're accessed commonly enough, they just never leave flash, right? Because we only release space when the pool gets above a certain fullness threshold. So we can do the mirroring in advance and then only release the space when it's needed. And so if the pool doesn't get too full, you know, and only old files are falling off the end and they don't get used very often, so that feature doesn't get used as much. But, you know, there have been, you know, I'll admit, there have been issues with hot pools, mainly related to, you know, processing change logs and things like that. And then, you know, the agents stop doing the mirroring and things like that.
The only thing to add is this has been from early versions like about 18 months or 2 years. It's been around, so it's not new by any stretch.
Another question?
We do have a big problem with the going from cold to hot pool part of the hot pooling, which frequently trashes shared libraries, for instance, or singularity containers. We have a DDN support case for that, but there's no progress. Turning off the heat function in hot pool removes the problem. Immediately when we turn it on, we get problems with shared libraries on some clients being trashed and on other clients at the same time being perfectly okay. Something we really would like to get sorted, but we haven't been able to get a trigger for it. But we need to look into that again sometime.
Thank you. Any question on mine?
Yes. If we lose the pools, can I/O be gracefully redirected to the disks?
I'm not sure. I mean, this is based on the PFL mechanism, so...
Yeah, so the question was, if we lose the flash pool, can the I/O go to the disk pool? And that's a functionality unrelated to hot pools, more related to the file level redundancy. And so if FLR, if the OST is offline, it will try to, you know, it will try to pick the mirror copy of a file that's on available OSTs, and so that is working, but we don't necessarily, hot pools is more of a caching mechanism, it's less of a redundancy mechanism, and so not necessarily all files will have a flash and a disk mirror, right? So if you know, newer files are more likely to have, you know, two copies of the file, and so, you know, it can improve the redundancy, and especially for like checkpoint restart, you're very likely to have two copies of the file as long as the, you know, restart is in a, you know, long enough time after the original copy was written that you would have the mirror copy created. Usually the delay is about 10 minutes by default. And so, you know, after 10 minutes you would have two copies, and if OSTs go offline, you would actually have increased availability of the data, which is good for the restart part.
Thank you. Okay, thank you, Sébastien.
Sure.
Last question. Sorry. Not yet.
We have one of those, no, we have two actually of those SF18 case, and we have 4 metadata servers. Could this hot pool functionality be added to our DDN system, or do we need to buy a new one to have this functionality?
So which version you said?
We have the SFA18K,
yeah, but
with embedded OSSs and the exascaler. I don't know. I don't remember the exascaler version, but
at least what I can say is that thanks to the you know, scanning capability. Where is it? Anyway, thanks to the new capability for Lamigo to be able to scan on already existing MDT, then I guess at least this does not prevent you from using HotPulse on an already existing file system. Yeah.
And it
Why
wouldn't conflict with the, if we already are using PFL, will it conflict somewhat? No. Thanks.
Thank you.
Sure.
So it's the end session of the first day. So you have understood this evening we will have the social event. I have just a few words about. Here you are. So remember, your badge is mandatory to have access. We have an appointment at 7. The address is Paris Yacht Marina à Port de Grenelle à Paris, of course. Quick planning. We start at 7 with an aperitif, and after that, dinner will be served at 8. So we have 1 hour where we can discuss together. A quick map, you have some flashcodes on the brochure, but it's just to show you the path. You have many ways to go from the conference to the social events. The plan A is, I don't know, but I think we have some Météo France guys in the room. If the weather is fine, I don't know. Walking is well for health, so it's about 30 minutes walks. The plan B is in the ground. You can take the line 9 from here, and you have a connection at Trocadero, and after that you can take the line 6 up to Birnacheim station. Plan C, what you want. Thank you. See you at 7.